And the term accompanying components refers to the elements that are not intentionally alloyed to the material. An accompanying element can be present in usually small quantities in metal. The presence of an element negative affects the property of the and special cases, some accompanying elements also exist as allowing elements in order to specifically change certain properties. The main elements are still chrome, nickel, manganese, silicium, vanadium, titanium, beryllium, cobalt, and Wolfenstein. Comparison of transformation behavior to alloyed and unalloyed steel. So it's time temperature transformation diagram for continuous cooling of this steel, and TTT diagram for continuous cooling of alloyed steel, chromium and aluminum. Next to the chrome, evenness, chrome is the most common element in steel. Ferrite formal extension of the format is good diagram by shifting the phase boundaries and reducing the parallel cross rate of 12%. Chromium are the net area is completely constricted. Reduction of the critical cooling rate requires formation, increases hardenability. Chromium forms carbides, increasing resistance. Nickel doesn't form carbides, but is always present as substitution cell solution in nickel has a grand refining and toughness increasing effect. Nickel forms nickel sulfur in the steel, which melts at 645 degrees Celsius. Red shortness substitution with serum and hardness to serum. So, obstinate formula, nickel extends the obstinate phase area here. Nickel lowers the critical cooling rate for particle formation and hence tough hardening. Influence of accompanying residual ramp elements in steel. In general, so elements which present small quantities can be expected mainly in the form of precipitation. This concern grain growth, phase transformation, diffusivity, toughness, compatibility, effects depending on the distribution. Uniform distribution of cumulative accumulation of constraint gradients, so the change of hot and cold formability, toughness, and precipitation, different effects depending on the distribution of precipitation, and follow preferentially at the grain boundaries. Effect in steel. Cold formability, aluminum, nickel, cuprum, aluminum, phosphorus, sulfur is what are used. Cold formability, silicium, cuprum, aluminum, nitrate, nitrogen, formability and hardenability, carbon, chrome, molybdenum, silicium, manganese, nickel, chrome, cobalt, bore, vanadium, titanium, carburization, the aluminum, chrome, copper, lead, strengths, aluminum, titanium, and others, or darkness, appropriateness, or machinability, or grain size, and wear behavior, aluminum, calcium oxide, silicium, titanium. Here we have a word about designation standards of stainless iron. Yes, literature you can use. So alloy steels for which the threshold values of alloy steel are exceeded for at least one element chemical composition. And here we have four main grades. In this case, one for a dot is the material main group. So zero is cast iron, one is steels, then we have two numbers, killers, and so on. Until number 9. 72 is a steel group number. Next slides, 25 steel grade number. Within a steel group, which is represented by some number, and additional symbol for further description, characterizations. Here are group numbers for alloyed steels and all steels. So on. We have types of aluminum alloys. State plans, systems, locations. Situation instance prefix. The change in shape is retained only as long as the external load is acting. Relieving the force of the object restores its original shape. Reasons for allowance is the reversible displacement of metal atoms from their equilibrium position. So we have this F is force, attracting force, repelling force, distance R, maximum distance, R0, equilibrium distance. Metals with high melting temperature, high binding energy, also usually have high loss elasticity. Have the slow, so stress with the F by area is equal to Young's modulus in gigapascals times elongation. So it's a length by initial length. Metals can be deformed by irreversibly displacing the atoms of the crystal. However, deformation only takes place in certain direction and planes. sleep planes and sleep direction. However, not all items of plane displaced. The formation is based on the movement of this location. Sleep planes and systems. Sleep planes without planes atomic layers with densest closest packing large plane spacing. As this location movement takes place in these planes during the formation, so the relatively smallest critical shear stress required. Sleep system describes the formation of metals by means of sleep planes and sleep directions. During plastic deformation, those dislocations are moved. Those sleep planes, the maximum shear stress prevails. Slope systems in the face-centric crystal structure have a C directions. So face-centric cubic all close back slip planes. One, two, three, four. C close back slip directions. 1, 0. 12 independent close back slip systems. Plastic probability. The eccentric crystal structures. At 1248 possible slip systems. BCC grid less dense packed slip systems than in FCC. This deformability is lower than the FCC lattice. And for these 48 sleep systems, only 12 are mainly activated. The other less favorable planes are activated in the event of higher extreme stresses. Sleep systems in hexagonal crystal structure. One closed packed plane, 3 independent sleep directions, so 3 independent sleep systems. Less densely occupied planes can occur in sleep systems if this direction is included. Few possible sleep systems, for instance, no plastic deformability. Here we have systems, sleep system overview, structure, splitting, CFCC, numbers of direction per level, numbers of levels, sleep planes, sleep direction, sensitive. So it is representing their distribution of the lattice. Dislocations origin during crystal growth from the melt during crystallization as a result of residual stresses. Both types of dislocations. There is an edge dislocation, shear of a rope perpendicular to the force. So here, at the site of dislocation, additional atom half plane that has no continuation on the opposite side of the crystal. And screw dislocation, shear of a rope parallel to the force. The glide starts to the front surface and continues step by step through the crystal to the back. And of an edge dislocation. The displacement movement requires much less force or stress as if all atoms were to shear simultaneously. The theoretical shear stress is much larger than the real critical shear stress. An atomic movement takes place only in a very small scale. This type of movement of a state dislocation is called conservative. This dislocation is Kontov's vector characterize the dislocation line. One compares the perturbed lattice using unperturbed lattice by continuing the steps around the dislocation in each direction from atom to the next. Subsequently, exactly the same steps are repeated in an undistributed lattice, but in this case the ring is no longer closed. This gap is determined as a Lorentz vector. This vector of step dislocation. Area is lattice disturbance. So Bor's vector is perpendicular to the dislocation line. Dislocation line and area without lattice disturbance screw dislocation. So here's its location line of screw dislocation. And here's a box vector. Screw dislocation, book vector slice parallel to the dislocation line. There is no clear plane. Crystals and crystals. The simple crystals, classic deformation due to dislocation movement takes place in slip systems with maximum shear stress. Single slip, only one slip system is activated. All crystals, crystallite orientations are literally aligned. In low range, plastic formation occurs in favorable oriented slip systems of a single. In high load case, microplastic deformation requires activation of less favorable slip systems. Then, sensing mechanisms, recovery and recrystallization. Strengthening or hardening. The purposeful uses make it possible to achieve this material properties resistance. Case the performance of metal, for instance, springs, or can be detrimental embrittlement in some cases. Recovery and recrystallization. Recovery and recrystallization can extend the probability of a metal as a counter effect to rock hardening. These phenomena play an important role in extending probability in industrial applications. So, intermediate annealing after cold deformation. Strengthening or hardening mechanism. How can a metal be strengthened? So, obstruction of the dislocation movement. Foreign atoms, solid solution strengthening, dislocation, work hardening, chain boundaries, free boundary strengthening, external phases, precipitation and dispersion. Strengthening due to grain boundaries. Grain boundaries are obstacles for dislocations. A dislocation cannot cross grain boundary. There is dislocations that are held up because the dislocation power to the repulsive force, the subsequent dislocation. Here, with a slip plane, grain boundary, dislocation power. The finer the microstructure, the more interface are available, and the higher the strength of the material. Strengthening by impurity atoms, solid solution strengthening. Solid solutions have a higher wild strength for metals. It's more difficult. This is this can be used because atoms of the added elements have atomic diameters deviating from the matrix lattice, which distorts the lattice more or distorts the lattice to a greater or lesser extent. On the other hand, small foreign atoms can accumulate close dislocations, counterclouds, and thus hinder dislocation movement. So we have here compressive stresses, post dislocation, tensile stresses. Transformed by the interstitial impurity atoms. Solid solution strengthening dislocations surround themselves with foreign atom clouds, collateral clouds. A sliding dislocation must drag these clouds along or break away from it. These effects are associated with increasing energy consumption. This results in a strengthening effect of solid solution element. However, sufficiently high strengths cannot be achieved by solid solution strengthening alone. Particle strengthening, precipitation hardening, extraneous-based precipitation can hinder dislocation movement very effectively. So strengthening, cutting mechanism and circumvention mechanism. Here we have once again a shear mechanism with dislocation, our shear force, precipitation. This goes dislocation to move with the slip planes. Dislocation move through the precipitation. In the shear mechanism, precipitation are sheared or cut by the dislocation. The shear in the precipitation takes place in steps, one Bruger's vector for each passing dislocation. In this process, two halves of the particles are reversibly shifted against each other. And here we have circumvention mechanism called orbital. So dislocation, precipitation, shear force, dislocation due to external shear force, immigration dislocation is stopped by a particle in slip level. Next dislocation are built up to a foreign phase. The fusion movement on the dislocation requires a higher stress strengthening. Fusion movement of the dislocation line opposite oriented dislocation segment attract each other. Precipitation annihilation and dislocation rings means around the precipitation. A free sliding dislocation can move on. Precipitates that are not coherent with the matrix lattice cannot be shared by dislocations because the phase boundary acts like a grain boundary. Influence starts. As we have seen before, there is a circumvention mechanism delta omega equation to square of d pi particle diameter, a small particle diameter, increasing shear stress, strengthening, and we have shear mechanism, Friedel, so delta omega proportional to 1 divided by particle diameter. So large particle shear is embedded, so there is strengthening. So we have circumvention mechanism curve, shear mechanism curve, particle hardening crisis. Muted dislocations or hardening. A cold forming temperature below the crystallization temperature results in the work hardening of the material. The cause of the increase of dislocation density is increasing deformation and the partial hindrance of the dislocation, their movement. So we have stress, elongation. So recovery and recrystallization. Cold deformation, strong increase in dislocation density. Strength increases, decrease in plastic deformability. Low temperatures, this thermodynamical not stable state, so condition is maintained. Heat treatment after cold forming, partial restoration of the original properties, recovery and recrystallization. So recovery is the rearrangement of lattice defects. Grain boundaries remain preserved. Heuristic cue for recovery, climbing of edge dislocation, cross slip of screw dislocations. Recrystallization, complete macrostructure reconstruction. New grain boundaries. Recovery and recrystallization are thermally activated processes. Conservative dislocation movement climbing. Edge dislocations, focus vector perpendicular to the dislocation line. Climbing of edge dislocation increase their volume. Climbing allows dislocations to leave blocked slip planes. This type of dislocation movement is called non-conservative. Diffusion is a thermally activated process. Cross slip of screw dislocation. Focus vector and dislocations line don't span a plane. So that means dislocations are not pointing to only one slip plane. Screw dislocations can leave their slip planes due to cross slip. So here is a line vector of the screw dislocation, cross slip, and Borger's vector. Recovery, dislocation, annihilation, and polygonization. So polygonization, due to the climbing of cross-sliding, two processes can occur that are crucial for recovery. Arrangement of edge dislocations with same sign and in small angle grain boundaries. Annihilation of edge or screw dislocation with opposite sign. Recovery dislocation, annihilation, and polygonization. Organization in or sub-boundary boundary formation. Start of recovery, cross screw dislocation, formation of cell structure by dislocation, annihilation, rising temperatures, climbing of edge dislocations, further development of cell walls. From the cell wall, the subgrain boundary is found. Well, here's the subgrain boundary, edge dislocation. Recrystallization. Principles of primary recrystallization. Deformed grain with crystallization nuclei. Grain growth on and recrystallized microstructure. So here's a low concentration of dislocations, recrystallized grain, large angle grain boundary, direction of grain growth, dislocation, rich again conform structure, and dislocation. Annealing recrystallization diagram. So here is secondary recrystallization using grain size in millimeter square, thickness reduction due to the rolling, and temperature. Annealing is constant. During cold deformation, internal stress are generated and the material becomes brittle. Excessive deformation can therefore lead to failure, fracture, crack of component. Intermediate annealing, so between the deformation steps, can cause the microstructure recovery. After this, further forming can be carried out. During the hot forming, recrystallization already occurs as a process. Dynamic recrystallization. This makes very large deformation degrees possible. Hot forking is therefore a very effective process for generating large shape modifications. And the last part is non-metals, ceramics, and glass. So ceramics, due to the special properties of ceramics, hardness, wear resistance, this material is indispensable for many applications. However, knowledge of the disadvantages like brittleness is also important for optimized material selection. Glass plays a major role in everyday life as well as technical applications like ceramics, as these materials completely different properties than metals. This must be taken into account for practical use. So ceramics we use in applications where high hardness, great wear resistance, high corrosion resistance, good temperature resistance, low thermal expansion, and low weight is required. The disadvantage, no plastic deformability. The ceramic materials are inorganic and non-metallic. As a rule, they are formed for a raw mass from a room temperature and obtain their typical material properties by a settling process at high temperature. Ceramic is macrostructural constituents less than 0.1 millimeters, and coarse ceramic is constituents larger than 0.1. Here's a classification of ceramics. We have organic and inorganic, organic natural, wood, leather, natural fibers, resins, uh, organic and synthetic, plastics, synthetic fibers, slides, synthetic resins, inorganic, metallic, iron, steel, ferrous metals, special alloys, and inorganic mineral, natural stones, binder, glass, utility ceramics, technical ceramics. According to application areas. Structural construction ceramics used for mechanical loads, industrial engineering ceramics. So there is a functional ceramics, electroceramics, cutting ceramics, bioceramics, and advanced ceramics. And the oldest group is silicate ceramics. Side ceramics, monoxide ceramics, nitrite and carbide ceramics, vessel structures, I'll quickly some tasks. So here is file without the answers. Just tasks. Yes, six answers. First question, we have metals, iron-based metals, and non-ferrous materials. In first we have steels, iron casting materials, have heavy metals and non-ferrous metals, light metals, and in group 2 we have non-metals, natural materials, synthetic materials, and composite. So 3 types of steel: structural, cool, quenched, and tempered. 3 types of cast material based on iron: cast iron, malleable iron, cast steel. Heavy metals: copper, zinc, lead, light, aluminum, magnesium, titanium. Natural materials: asbestos, wood, granite. 3 examples: man-made materials, synthetic plastics, glass, ceramics, composite, reinforced plastics, hard metals, plywood. So density limit here is 4.5 grams per centimeters cube. Is negative charge in atomic shell, proton positive in atomic nucleus, and neutron in atomic nucleus. Atom total charge is neutral. So here we have attraction force as a result force. You see the coherent force, H0 equilibrium distance, repelling force. What is mean to stable unit cell? The unit cell describes the regularity of the atomic order in 3 special directions. 4 different two-dimensional lattice defects. So large angle grain boundary, twin grain boundary, staking error, and small angle grain boundary. So what do we call about dimensional lattice defect? Dislocation line effect. What are steps to solution? Substitutional solution and interstitial solution. Stem crystal mixture means alloy with several types of crystal. So phase alloy summary of all areas of system with specially constant physical and chemical properties. State variables are temperature, concentration, composition, pressure. In what state is such a system if state variable don't change in thermodynamic equilibrium? So what role supercooling, superheating play for solidification, melting, or metallic systems respectively? What happens to the system thermodynamic equilibrium? It's melting, solidification, temperature, solid and liquid phase and exists simultaneously. For instance, liquid water and ice, 0 degrees, no phase transformation occurs. The system is in thermodynamic equilibrium. Solidifications, therefore, a temperature is required, which is below the equilibrium solidification temperature, supercooling, so that salt can solidify on a temperature which is above the equilibrium melting temperature, superheating. was it? Solid or not? Mesh system miscibility gaps occur in heterogeneous systems. What is a miscibility gap? Splitting gap occurs when a certain range of composition atomic species A and B doesn't mix or blend completely in a single phase. They don't form a solid solution. There is a mixed phase, mixture of two different phases occurs, so mixture of alpha and beta phases. Associated the diagram of glucose below inserts following terms. Solid solution, liquidus line, solidus line. Here the task. Here we apply a double rule. Sketch the mass transport of A atoms to B atoms in front of a reductive solidification. Yes, alpha, beta, zero. So A to alpha and B to beta. We here a sketch microstructure for different temperatures. Space. So what is the range room temperature called? Gap. Scale heating, crystallization, quenching, Martensink transformation, and tempering. Annealing, quenching, rapid temperature drop, artificial and natural etching. What is particle minimum? Components, hazard, alloying elements. Three main grades of steel: unalloyed, stainless steel, and unalloyed. Stable solidification carbons bonds cementite. Stable solidification carbons present as graphite. Eight percent aluminum, 1% magnesium, small amounts of silicium and copper. Critical alloys, and the groups of rough alloys, auto hard, naturally hard, precipitation, iron alloys. T. Oxlow. Which latest has the most leading systems? So it's a BCC, 8 systems. Cells, center cubic, hexagonal. Second vector is edge dislocation, perpendicular is screw dislocation, parallel vector. So that is forms linear perturbation of the lattice. Shear mechanism, always rejoin and slightest effects, crystallization, completing reconstruction. So that's all. Well, thank you for watching this lesson, and this is the end part of material science.